So welcome. This topic is going to be, let's say, an application, a practical application, and the organizers have been warned, so there won't be super lot of details about GPUs, but I will try to concentrate on those facts too. So the aim here is that we want to do a real-time 3D video conferencing. Obviously, the 3D is new here. Video conferencing has existed for some time now. And what I'm going to talk about is just video conferencing in general, what kind of technology we want to use to make it 3D, namely light fields, how do we capture these light fields with cameras, how we convert it to the light field that we can display, and of course, also the displays, and the prototype system that we built, and I will finish with some discussion. All right, so let's go for video conferencing. We all know that Skype has existed and had a video conferencing feature since 2005. But let's just go back more in the past. We could treat the Apollo moon landings as the first interplanetary video conferencing, right? Of course, it was one way, but still, it happened in real time. But if we go further back, already in 1936, in the German Reich Postzentralamt, there was basically a service that between the major post offices of Germany, you could go into a room and there was like an analog TV solution there, and you could talk to another person in another city. It was kind of before its time. And there were already some analog TV-based solutions in the Bell Labs in the 1920s in an experimental stage. And just to be even going back to the past, there was this artist concept that they imagined that in 2000 people would be able to just talk to another people. And it's somewhat accurate, I would say, that they figured out how projectors might look like. And okay, well, they had their limitation. But so, video conferencing, we want to capture something real. We want to process or compress the data, transmit it, and decode it on the other side and display it to an actual human being. And let's go for light fields. So if you want to do 3D and you want to do it without glasses, there is this technology called light field, which basically you just treat light as a vector field around you. And a very useful subset of this vector field is if you take like a window and you just measure what kind of light goes through it from one side to the other. And of course, if you can recreate that light, then it doesn't matter if reality is behind that window or not, you are going to perceive it as a 3D scene. Of course, for this, every pixel of this display has to emit different colors of light into each direction. Well, this is not very practical, so let's just go for horizontal parallax first, and let's see how 3D displays there work. So horizontal parallax means that you get a different view if you move in a plane, but you're not going to get a different view if you're moving in the other direction. But humans tend to move on planar surfaces, so it's fine. And you could view this as you have a screen that, let's say, elongates light along this dimension. So it doesn't matter if there is a short person or a tall person, they are going to see the same image. And behind that, you are going to have projectors, let's say. And if you want to create a virtual point here, you just project these certain light rays, and then people behind this screen are going to perceive this point there. And of course, from all these points, you can build up your whole 3D scene. Yeah. So this is just a TV screen that is going to give different views into different directions in a horizontal way. And of course, your left and right eye are going to perceive a different image that is perspectively correct for the scene that is represented there. So this is basically autostereoscopy. You don't need glasses, you're able to move. Multiple group, a group of people is able to be in front of the TV, and they can even point into virtual points, and then they see that as a seamless interaction with 3D. And of course, yeah, you can have it in a kind of a cinema format or a TV format. It's just the mechanics and the arrangement of the projectors in the screen. So if you want to do a human-sized display, because we want to transport a human from one place to another, then this might be an arrangement that, of course, you take a 9:16 ratio, because, of course, there are projectors behind it, just in the 90 degrees orientation. And, of course, field of view is very important. You want to have a group be able to really move in front of the display, so you want to generate obtuse rays. But a useful trick there is that, so behind this image there is a projector arc, probably like 80-some projectors. I forgot the exact number. And this is the hollow screen that you're seeing here. So this is a top-down view, basically. These are the mirrors. And yeah, so based on this mirror, you can just imagine a virtual projector here, and then basically you get the obtuse rays and get the wide field of view. All right, so this was easy so far, but how do we actually capture light field? Because, of course, if you have a virtual scene, you can just ray trace as many rays as you want. But in a real-life setting, you actually need cameras in all the positions where you are interested in how that scene looks. There are approaches when you are looking at a scene from a limited number of positions and try to compute the intermediate ones, or generate the 3D model and based on that compute any direction. But these will be always flawed, because in a real scene you are going to have translucent things, specular things, and you cannot really predict the color of an object from an unknown view. So popular camera arrangements, of course, linear or circular, based on where you are taking your cameras. Of course, linear is often easier because it just makes your algorithms more regular, more on a grid, but circular is better for like field of view, and you need less cameras to capture your scene, and you also have the ability to view it from different angles. But of course, in practice, this is really, really tough, because you might have a lot of cameras, but it will always be an inefficient way of capturing a scene, because you have a lot of information at the position of the cameras, because cameras usually capture like 2K, 4K, and you will have 0 images between the cameras. So we have to treat this some way. And of course, a calibrated camera system is much easier said than done, because we have to have a whole range of information about these cameras, like where they are looking at, what exactly their field of view is, what kind of lens distortions they are having, what kind of color balance or information they are capturing exactly. And just to illustrate the difficulties in this, I cherry-picked a few distortions. So when you just take a picture with your smartphone, you imagine it as a regular grid of pixels, everything is fine. But when you want to do anything objective or like quantitative with the images, you have to treat all these distortions. Yeah, pincushion, barrel, because the pixel grid is not going to be regular in reality. Pixels might even be slanted, which is a very weird feature, but it happens. And of course, the lens and the image sensor might be misaligned in very weird ways. And in order to compute all these distortions, the usual method is to take a chessboard with some known parameters, like a regular grid of points. You move it in front of your camera as many times, and then in each image, you know that that regular object is there, and you just use complicated linear algebra with some tolerance for noise to compute all the parameters of your camera. And of course, we have to do it for many cameras and preferably at the same time. So this is kind of how it looks in reality. This is our camera arc that we implemented for this project, 96 gigabits Ethernet cameras. And of course, we need to have small size cameras so we can pack them densely, so that there are few actual gaps between the cameras where we have 0 information. But of course, the smaller the cameras you have, usually they don't have a good image quality, let's say. Their color might be off a bit. They might have good resolution pixel-wise, like the number of pixel-wise, but of course, you know that megapixels are less important in cameras than their actual quality. And of course, you want to minimize costs, or like at least keep it at a reasonable level. The problem is that even the cameras that are like more than 100 and less than 1,000 euros, they are still very bad in quality. And they are usually just these industrial grade cameras that are usually used for like surveillance or like just recording like rooms and stuff. And of course, an important thing here is that you never ever want to have a lot of USB cameras plugged into your computer because you don't know their order. And then every boot up, it just randomly orders it. So you will have to figure out which camera is which. But with gigabit Ethernet, you can assign at least addresses to them. Yeah. And this is this checkerboard I was talking about and our calibration system, where we are just taking pictures from all cameras. And the checkerboard is standing roughly where the person should be standing. Okay, so now we have displays, we have cameras, and how do we get the connection between them? And how do we convert between the two light fields? The problem here is that basically each display and each camera system has a unique set of rays that it's able to capture or it's able to emit. So you can view the whole thing as there is reality, that's a voodoo doll, and you have a capture system that you pin random blue needles on this voodoo doll, and you have the display system, which is just random green needles in this voodoo doll. And you know what you have and you know what you want, but there is no clear connection between the two. So it's just a huge 4D interpolation problem, basically. And like if you have one ray that you know, and if you have another ray that you know, but you have a ray in between them that you want to compute, there is no clear strategy of assigning the weights of this interpolation, because you don't know at which depth they are supposed to intersect, or they bump into the actual surface that you captured. And yeah, so basically the next slide is that you could add depth sensors into your the camera array, but this is a flawed concept because depth sensors are usually lower in resolution. They are noisy, they have temporal flickering, they have occlusion problems, and just as a sample image, look at this person's hand. There is no very clear boundary between the foreground and the background. And there might be pixels that are a bit flickering between the foreground and the background. And this is going to be extremely immersion breaking for a visual experience. So having a uniform blur over the whole image is better than having a relatively good image, but with some flickering and in some sensitive areas, because your eye is just going to focus on them and will destroy your visual experience. Yeah. So let's go for the prototype system. Well, this is the schematic. Cameras, there is a camera aggregator, which is in the current state is just basically a power over Ethernet switch that just collects all the information from the cameras and then pipes it through a LAN, which currently is just a fiber optic due to the immense bandwidth requirement. And on the other side, we just have the distribution of all these camera streams to the slices of the light field processing units that we have. In practice, this means maybe 8 computers and 20 GPUs processing the data and then sending it to this 80-something projectors. And of course, if each GPU has to utilize all its outputs, basically. And it's a huge challenge, actually, to find a GPU that has the exact outputs that we can connect to the projectors that we purchased for any given system. And so these are the technical parameters. Yeah, the 96 cameras, they are in a 120-degree arc. And currently, we don't use compression to minimize latency. And on the other side, we have 100 megaarrays in order to get, for each view, its own image, and then to get the 3D, of course. And the field of view is almost 180 degrees. And you see that there is a mismatch. Well, this was a technical goal of this project to have a 180-degree display, but it wasn't practical to build such a camera arc. So in the remaining field of view, you just get basically a 2D image. Yeah. And the combined latency is 100 milliseconds to pipe all the visual information through and then display it in the end. So, but we could use compression, but it's a big bandwidth versus latency trade-off. That if we would use the existing technologies like NVIDIA's this NV decompression and NV incompression, it would add around 30 to 40 millisecond latency. And of course, we would also need to use computers on the capture side and their equivalent GPUs. But that would actually be at least real time. And there are a lot of research in this area of jointly compressing camera streams because like cameras that are next to each other, they don't quite have a substantially different image, of course. But all those joint compression algorithms are not real time or they don't have hardware interpolations and yeah, they are out of scope for us. But so with this, we could actually do not just a LAN solution, but an internet-based solution. Of course, you have to add also the network latency on top of everything. So how does this really look? Well, we started with a girl. We have to end with a girl. This is the wife of one of my colleagues, and she's standing at the focus of this camera arc, and these are 2 images just from the display. And you see that like she is looking sharp in these images, and you can imagine based on the 2 images that it's really 3D. But the background, for example, where we had the checkerboard there, is very, very blurry. And this is because since every camera is focused on the person, or where the person is standing, that's where we have the highest ray density of captured rays. So we have less information from the far background or the far foreground. And it's also true for the display that the display's emitting ray density is the highest at the plane of the display, basically, or the plane of the screen. So this is a compounding effect that anything that goes far out or far in is going to be blurry. So you could view light field as an inherently volumetric technology based on this. And just so that you believe me that this is really 3D and it's happening. Yeah, so this is just a handheld, basically a video camera taking an image of the 3D display. I mean, unfortunately, we directly sold the prototype after taking these images. So we cannot really have any better demonstration based on this, but yeah, that's what we have. So currently the prototype is actually in Seoul, in Korea, in a hologram conference room exhibition center. It's a bit like the Hungarian Csodák palotája, just to demonstrate new technologies and show people how the future might look like. Yeah. So let's go for discussion, like how useful is this in reality? There are some obvious drawbacks that so far I presented you a one-way video conferencing system, but everything should be two-way, or this is what we expect. But the problem is, where do you put the cameras if you have the display in front of you? And this is a bigger problem than, let's say, for the laptops where you have just the camera on top, because like if you have a full human-sized display and you have the cameras on top of it, it would create this slanted perspective, and it might be uncomfortable. So some kind of, we might have to use some different display technology where you can actually insert cameras in the display, or do some gaze correction or view synthesis to compute how the person might look like from this display's point of view, or do some other light field interpolation tricks. But this might not be solved in the near future. But the bigger problem is that I looked at Wikipedia, like what are the big problems of video conferencing systems, like why they are not adopted that much. And this is the list that Wikipedia came up with. And I have to be sad to admit that none of these problems are going to be solved by 3D. Like, we are just increasing bandwidth, we are increasing complexity, we are increasing technical difficulties with this. So far, this is an eye candy rather than any kind of productivity increasing solution. Yeah, and acknowledgements, this work was supported by the EU, and yeah, thank you.
Any questions?
I've seen that you have a problem with compression, and I don't know if you heard about Binomial. It's a company, they are, I think, the state of the art for compressing images and textures. I think that could be good for your compression problems. I don't know if it's still a big problem or it has been solved already, or I don't know if you can answer that.
Could you repeat the name, please?
Binomial. It's called Basis. I think it's getting into GLTF now. I don't know if it's already in, but it will get into GLTF.
I will look at it. Thank you.
Welcome.
Any other questions? I had one. If you said that blurring is still better than having flickering by not knowing having a lower resolution in the depth data and the pixels jumping in front. But doesn't video compression provide you with an automatic blurred image? Like if you are not compressing in a very high bitrate, but things start to become like lower resolution, isn't that sort of like a blur that you get for free?
So currently we are not doing compression of any kind. We're just doing the mathematical conversion and displaying the things. But the blur you're mentioning is a rather low level. Like, if you remember the chessboard, it was really a visible kind of blur that you had these multiple views kind of overlapping on top of each other. So it's a different magnitude in that case.
Okay, true. Any other questions? If no, then let's thank the speaker again.